In this video, we'll be talking about the chi-squared test that looks at the independence of two or more categorical variables called the chi-squared test of independence. Again, with this test, we're going to be looking at multiple categorical variables, two or more, to determine if they are unrelated from one another or independent. Under the null hypothesis, which will be that the variables are independent of one another, the value in each cell is going to be the row total times the column total divided by the grand total. So this is the expected value. And this is how we're going to find, again, we'll have the observed counts. This is how we're going to find the expected counts within each cell. The test statistic and chi-square distribution are going to be the same as we've discussed before. And if statistically significant, this means that the variables are not independent of one another. That is, that the values of one variable change based on the values of another. Another way to say this is that they are related. They are dependent. Again, there is a relationship between the two. So if I think about males versus females, and do you prefer chocolate versus vanilla ice cream, a categorical independent variable, males versus females, and a categorical dependent variable. If they were unrelated, that would mean that the preference of chocolate versus vanilla does not relate to the person's sex. So males have the same preferences as females. But if there is a relationship, that is, if the variables are not independent from one another, then we would expect different levels of chocolate versus vanilla preference for males than females. Now, we're not saying that there are more males than females. That's not the test. What we're really looking at is, in a way, the percentage when we only have two outcomes in the dependent variable. So, for instance, what percentage of males prefer chocolate versus what percentage of females prefer chocolate? And in that particular case, if the percentages were different, then the counts within the chocolate versus vanilla variable are going to be different than one another. So in a way, we're starting from the percentage is that all of the percentages are the same in the male and female group. Now, that is phrased when I have an independent variable and dependent variable. Chi-squared can be used to test even when we don't have independent and dependent variables. It can be used to just test general relationships, which is why this is phrased so generally, is because we don't necessarily need an independent or dependent variable, but sometimes it's easy to forget how the test of general relationships can then relate to independent and dependent variables. So that's one way that those can relate. All right, so believe it or not, we actually already have all of the information that we need to run through examples. Recall that previously we have our observed tables. We calculated expected values in the previous video in this lecture set. We calculated them using pre-specified null hypothesis proportions. In this test, that was for the chi-square goodness of fit test. In the test of independence, now we're going to calculate them using tables and using the row and column totals, again, multiplying them together, dividing by the grand total. That's going to be how we get our expected counts. And then we're going to do the same thing, observed minus expected squared over expected. So we actually have all of the different components that we need to run this test already, just with that one slide, because really the only thing we needed to figure out, as we already knew the component from the chi-squared distribution, we already knew the component from the observed counts. All that we needed was to figure out the new way that we're going to do expected. And so that is how we are going to do expected here. So in this case, we're going to look at a similar example to before, but now we're going to test the different types of patients, how many patients come in which don't have an appointment versus how many patients come in which do have an appointment at alpha equals 0.05. Here, we're going to test if the hospitals differ in the types of patients they see. Now, it's very important to understand what we're doing and what we're not doing. We are not testing the same thing as we did earlier. That is, we're not testing the number of patients at each hospital to see if they're different. Hospitals having different numbers of patients will not impact this analysis. Now, it's important to acknowledge this with the other variable too. If we have more walk-ins than appointments or more appointments than walk-in patients, that also is not going to impact this analysis. That's not related. The different numbers within different hospitals and different numbers of walk-ins versus appointments overall is actually taken into account in this analysis. This analysis lets them be different. And again, doesn't judge here, but ultimately that doesn't contribute to a statistically significant difference. What this is looking at is the patient makeup per hospital to determine, is the patient makeup per hospital different? So if overall we have an average of 10% walk-ins versus appointments, so that's a ridiculous number, but if that's what we have overall, then that's fine. And if we have 50% overall, that's fine. If we have 90% overall, that's fine. What we're looking at is one hospital, or at least one hospital, different than the others. And again, if we have one hospital that has 50% of the patients and the other two have 25%, that's fine. That's not what we're asking. We're asking, is the makeup, the patient makeup at the hospital different? So be aware of what's going to contribute to this test. That is different percentages of patient makeups at different hospitals. That's what's going to cause this test to be statistically significant or contribute to statistical significance. Things that will not contribute to statistical significance in this are the number of patients per hospital and the number of walk-ins versus appointments. If those are different numbers of patients at different hospitals, that's not going to mean anything here. And if we have different numbers of walk-ins versus appointments, that's also not going to mean anything here. This is just going to test, are the percentages different for different hospitals? All right, so here we have a table. We have our walk-ins. These are actually the previous numbers that we used on the previous example for hospital A, B, and C. But now we've added the appointment patients, and at this particular hospital in this particular region, we have many more appointment patients than walk-in patients. Our null and alternative are going to be, the null is that the hospital and patient type are independent, and the alternative is that they are not independent. So you can actually see I'm using words to describe the cases here instead of writing out the particular equations. Now, as we discussed, to get the expected counts, we're going to be using the margins. Recall the equation, and I use the word equation lightly. It can be written mathematically. We'll talk about that in a second. But the formula that we had discussed in text is taking the row column, or the row total, adding up everything from the row, the column total, multiplying those two numbers together, and then dividing by the total of everybody in the table. So let's look at what this looks like. We have our margins where we have the total on the bottom. We have the total for hospital A, hospital B, and hospital C. On the right-hand side, we have the total number of walk-in patients and the total number of appointment patients. And in the bottom right-hand corner, you see we have the total number of patients overall. That is the sum of everybody in the light and semi-light green in the table, or the sum of the right-hand side values within our row totals, or the sum of the bottom column totals. All of these add up to this number. This is, again, the total of everybody in our table here, the grand total. So that's going to be our denominator. Again, the row, we're going to take the row total times the column total, and divide by this number to get the expected value. So this is all of our observed counts. Now let's look at our expected counts. All right, so for the top left, I take my row total, 274, multiply by the column total, 491, divide by the grand total, total number of patients in the whole table, 1,170. And my expected value for this cell is 114.99. And now I simply do that for every cell in the table. So for instance, let's explore this one, 232.81. This is taking my row total, 896, multiplied by my column total, 304, and dividing that product by 1,170 to get this expected value, 232.81. These are the expected values. And now we're going to use the table of observed values minus expected values, square that quantity, and divide by expected values, just like we had before. And we're going to do that for every single entry in the table. Now, there are 6 numbers in the table. I don't have room, unfortunately, on this slide to write them all out. This one that we see here is for the top left cell. This one we see here is for the bottom right cell. And I do this for all of them. So there should be 6. 1, 2, 3, 4, 5, 6. 3 in the first row, 3 in the second row. It doesn't matter what order you do them in. Just make sure that you are matching the appropriate observed cell with the appropriate expected cells for each of these. But as long as you're making that match, it doesn't matter what order you do these in. Looking at this, again, as we discussed earlier, I can see the components that are contributing more or less to the statistical significance. Here I can see that the one in the top left, we have more patients who are, I believe that this was walk-ins than we would expect typically in hospital A, and that this is contributing potentially more than any of the other values are contributing. So I could look at that if I have all these written out. Again, we don't tend to talk about that in our statistical story unless this is statistically significant. So I'm going to wait on that to determine if I talk about that until I've determined if this is statistically significant or not. But I can make a little mental note or just leave this written out. And if it's statistically significant, come back to this and say, okay, well, this number seems to be higher than the others. What does that correspond to? And in this case, that corresponds to the observed being higher than the expected. Adding all of this together, I get my test statistic of 10.4623. So now I can calculate the degrees of freedom. Recall this is I minus 1 times j minus 1. So I have I, the number of rows. J, capital J, is the number of columns. So I have 2 minus 1 rows, 3 minus 1 columns. That gives me 2 total degrees of freedom. We're going to compare, in this case, to a slightly different critical value than we had before. Now, I want to call out why this is different. The degrees of freedom is actually the same as we had before. But now, in this problem, in the initial problem statement, we had alpha given as 0.05 instead of 0.10, and that changes what our cutoff is. So this is a slightly different critical value, but it's slightly different because of the alpha level, not the degrees of freedom. And you can grab this value from statistical software or an online table, or a paper table if you want, from an old stats textbook. If you have one laying around, they all have chi-squared distributions in the back, and they would have this value listed in there. Because our test statistic is larger than this value, there is enough evidence to reject the null hypothesis. That's our determination. We reject. And what does this mean? Again, this doesn't mean that hospitals have different numbers of patients. That's not what we're testing. This doesn't mean that there are different numbers of walk-ins versus appointments. That's not what we're testing. Those two facts, whether they're there or not, don't contribute to this decision at all. This is evidence that the patient makeup at each hospital is different, that at least one hospital has a different patient makeup than the other two, or maybe all 3 of them are different. It doesn't distinguish between, but at least one is different. It does look like, again, when I compare the observed to the expected, and now this is okay. Recall that I couldn't go into those and break them out as I was doing on the last slide. That wasn't really appropriate unless this was significant. Well, now it is significant. And in the last case, it wasn't. So we said, hey, don't write this in your story. Now I might write this in my statistical story. I might say, hey, look, hospital A looks like it had a higher proportion of walk-ins than we would tend to expect. Hospital B looked like it has less walk-ins than we would expect. And you can go down the list and again see which ones contribute the most and then interpret those cells individually. Now, there's a lot of ways to describe this evidence. Hospitals serve different numbers of patients. Hospital and patient type are not independent. Patient type depends on the hospital. And that's a little strong because that implies causal language, but in this case may be justified because of the nature of the variables. Hospitals have different patient type. Different patient types go to different hospitals. Again, we want to be careful about using causal language because we don't recall causal language is established in the experimental design, not in the statistical analysis. But there's a lot of ways that we can summarize this finding. And again, ultimately, it's that the hospitals have different numbers within the categorical type of patient. And however you want to say that is a summary, again, as long as you're leaning away from the causal language. Do we know that the hospital causes this? Could it be some underlying or confounding factor that's causing that? Well, we don't necessarily know. A bad way to interpret this is, oh, my hospital's hospital A, we have more walk-in patients. It's because we're a way better hospital. That is completely unjustified. We may have evidence that hospital A has more walk-ins than other hospitals, but maybe it's because of location. Maybe it's because of a different version of location is just it's in a higher density area, so there's more people walking around hospital A than hospital B or C. But maybe equally, it's because the staff is more friendly and we offer better health care. Like, the statistics don't tell that. That's not what's observed from this. Any claims on that are just you making up stuff, which is not always necessarily a bad thing, trying to explain why this happened. But those explanations are not themselves statistically supported, right? The explanation part of the story, as we've discussed in the statistical storytelling, that should be set aside from the statistical results. The statistical results are that hospital A has more walk-ins. The explanatory stuff, the rationale for why that is not supported, at least not by this particular statistical analysis, and so should be made distinctly if this is the only analysis you're presenting, so that readers or listeners of your statistical story can understand this is your opinion as to why, or this is what you believe as to why, as opposed to this is what the data imply as to why, again, as the results from this particular analysis. All right, so let's look at the computer report for this. I see the chi-squared matches, thank goodness. The test statistic, the degrees of freedom are 2, which also matches. And again, this is something that I do check on when I'm checking this type of information, because I want to make sure that the computer read everything in appropriately, that the computer is analyzing everything appropriately, etc. And I can see, again, comparing the p-value to my alpha level in this case is 0.05. 0.005, 0.5% is smaller than 0.05, 5%. So I'm going to make the determination of statistical significance here. Again, the interpretation after we've determined a statistically significant relationship is the same as before. So the p-value and the critical value are just two approaches to make a determination of statistically significant or not statistically significant. Everything that happens after that is the exact same. All right, so now I'm going to give you some data based on the antibiotic data set. So this is, we have a couple of different types of practitioners, and I'll go on and tell you that this is not the actual practitioner types we compared in the study, that we did compare practitioner types. MD versus DO on the use of broad spectrum versus narrow spectrum antibiotics. And the caveat in this data collection is we did chart review to determine that either, or I'll say generally, either could have been assigned. So it wasn't a case where we really shouldn't have assigned broad spectrum or really shouldn't have assigned narrow spectrum. It was so far as we could tell, a reasonably preferential choice. All right, so what actually happened in the data is presented over here on the right. I will say these numbers have been slightly changed from the original study. The BS stands for broad spectrum, NS stands for narrow spectrum, MD stands for our training practitioner type, and DO stands for our training practitioner type. And so we're comparing the background of the practitioner and their degree in training to what type of antibiotic they are assigning. So what I want you to do is to, at the alpha equals 0.05 level, figure out if there's a relationship between this background training and which antibiotic is selected. And I want you to use this critical value. Try to figure out where I got DF equals 1. Maybe try to calculate that on your own and make sure you can follow along. And then the 0.05 is just the alpha level. Again, all of that goes in the upper tail because the chi-squared, as we're discussing it in this analysis, is always going to be an upper-tailed test. So make sure you can find where those degrees of freedom came from. Again, I'll give you the cutoff value, 3.841. And then go on this. Go on and give it a shot. Go on, pause the video, give this a shot, and then come back when you're ready. After you have calculated the we have the observed, calculate the expected values, calculate the chi-squared, test statistic, compare it to the critical value, make a determination about significance, and then write up what that means in the context of the problem. And then after you've done all that, so again, pause the video, do all that, and after you've done all that, come on back, and we will discuss the solution. All right, so coming back to this, I'm going to spread this out here so that I can go on and add in my margins. So when I calculate my margins, I get 416 and 513 as the column sums. And for their row sums, MD, I get 421 MDs, 508 DOs for a total of 929 participants in this study. Calculating my expected values, I get 188.52. MDs were expected to assign broad spectrum antibiotics, 232.48. MDs were expected to assign narrow spectrum, 227.48. DOs were expected to assign broad spectrum, and 280.5 DOs were expected to assign narrow spectrum antibiotics. Now that I have my observed and expected, I can go on and calculate the test statistic. Again, the formula is the same. Plugging all this information in, I get the test statistic of 9.6839. And if you're to within a couple of thousandths of it, a couple of thousandths of this answer, I would absolutely count that as rounding error. If you're like a couple of numbers off, then that's probably not rounding error. Maybe go back and double check your computations. Since our test statistic is greater than the critical value, this is evidence that we can reject the null hypothesis. That is to say, we have enough evidence to determine that the different educational backgrounds for these individuals is related to whether or not they assign broad versus narrow spectrum antibiotics. And do we want to say that that's the cause? Well, no, we don't necessarily have enough evidence for cause. Again, that's a research design issue. Depending on the design of the study, we might be able to say that. And the fact that the reverse causation, that assigning a particular type of drug makes you one particular degree or another, well, that's kind of an interesting direction to pursue now that I think about it. But anyway, we'll just leave this as not causal, say that the study wasn't set up to design cause, and just note this as a relationship between the two. Now, because in this case we have a dependent variable that has two different levels, we can actually compare percentages. So this is nice, and we could have done this one on the last one too, that when we have a dependent variable with two levels, we can look at the percentage of one. So in this case, for the MDs, I can count that we have 49.6% prescribed narrow spectrum antibiotics in their most recent antibiotic prescription, and 59.8% of DOs assign narrow spectrum antibiotics. Now I'll note I'm calculating this from observed, not expected. So this is telling me that, and in the expected, if I calculated this with the expected, these should be identical percentages. But in observed, I'm seeing DOs assign it 60% of the time, MDs assign it about 50% of the time. So this difference was found to be statistically significant. That's what we just determined. But remember, statistical significance is part of the inferential component of the story, but there's a lot more involved with the story. One of the questions in the story is that of effect size or practical significance or clinical significance. So is a 10% difference in the assignment of narrow-spectrum antibiotics clinically significant? And it may or may not be, depending on the context, depending on what you're looking for and what size impact you think you need to have. Of course, the other thing is which one is right. And this doesn't actually tell us, like, is it a good thing to have assigned narrow-spectrum antibiotics? Well, in the case we were looking at, we determined that, yes, this was part of the goal of the program that we were assessing at the time. But that's not necessarily implied writ large. Like, that's not something that you can necessarily that is detached from the story itself. So here, maybe it would be better to assign. Somebody could make an argument that's better to assign broad spectrum antibiotics. And again, my point isn't to debate that particular issue. My point is to point out the statistics don't tell you which one is necessarily right. They don't really contribute to that argument in a positive or negative way. You kind of have to settle that argument outside of these particular statistics or this analysis, and you may use other statistics for that argument, but that these statistics don't really relate to that argument. They simply discuss the proportion of rate of usage among two different groups with different educational backgrounds. So let's visit the computer report here. We can confirm our chi-squared test statistic that we calculated by hand. We can confirm the decision from the test using the p-value. P is less than alpha, so we rejected the null. And again, we have the same interpretation as before. I can also confirm the degrees of freedom being 1. And again, this is something I really like to do because that degrees of freedom calculation you can do pretty quickly and easily in your head. In this case, I have 2 columns. Minus 1 gives me 1 for I minus 1. I have 2 rows, minus 1, and 1 times 1 gives me 1. So I have 1 degree of freedom in this particular case, and I can quickly double check that to make sure this read in. And again, I have had it happen quite a few times where I've looked at the degrees of freedom for a particular analysis, even one I myself have constructed, and noted that the degrees of freedom didn't match what I expected based on the number of categories. And it turns out that either the software read in the problem wrong or the data was coded incorrectly. All of these issues can lead to, and again, as we talked about before in this class, and I hate to keep beating a drum, but in this particular case, and in all of these cases, it doesn't matter where the error comes from. It doesn't matter if the data were coded incorrectly. It doesn't matter if it was entered into software incorrectly. It doesn't matter if the data were coded correctly, but the software interpreted it incorrectly. It doesn't matter if the software interpreted it correctly, but it spat it out and I made the incorrect interpretation based on what the software said. Like, none of these things matter. The thing that matters is making the wrong or right decision. And if you make the wrong decision, it really doesn't matter as to why you made that decision. The harmful effects of having made the wrong decision are still just as harmful. All right, so there's a couple of closing notes I wanted to make. First is regarding assumptions. I mentioned there's no real assumptions, and distributionally that's kind of true. But what we do like to see is that most cells have expected values greater than 5 in this. And that actually, I guess, is in a way a distributional assumption, though it's not one we would normally think of as distributional, or you might normally think of it as distributional. That's fine. But think about having the expected values in most cells. We say about 80% of the cells should have expected values greater than or equal to 5. And so if you're there, you're good to use the stuff we talked about in this class. If the values are less than 5, it tends to be recommended to use a slightly different analysis that accomplishes the exact same thing called a Fisher's exact test. Now, in some software, let's say you're using SPSS, sometimes this is just a click of a button to say, actually, I don't know if Fisher's is in SPSS. Anyway, in some software, it's just a click of a button. I would check either the chi-squared box or the Fisher's box, or I could check both of them. But if you do have the expected values in several cells, more than 20% of your cells, the expected values are less than 5, it's highly recommended to use the Fisher's exact test instead of the chi-squared. Again, this test is very versatile. I like it a lot because virtually any other test can be reduced down to this, and this can handle more than 2 levels of variables. We saw that with 3 different hospitals, so I can do more than just 2 category or 2 groups within each category. You know, I can have 3 or 4 or 5 hospitals, and I can still run the test. I could have the 2 degrees MD, DO. I could do NP. I could do BN. I could have a whole ton of different. There's one other that we actually looked at, but I'm not thinking of right now. I apologize, but I could have a whole ton of different degrees that we could look at. And again, I can handle more than 2. Remember, the options are called levels. So in degree, I could have 4 levels or 5 levels. In hospital, I could have 6 or 7 levels, and I can handle that. So we showed that with hospital. We had 3 levels in the variable hospital. So we can handle more than just 2. And what we didn't show is I can handle more than two variables. We'll talk about that in a moment on the next slide, but that is a possibility with the chi-squared. This doesn't imply causality or direction. We kind of just talked about that. So that's an important thing. Important thing to remember here is, again, that's not something that is included with the chi-squared. I'll add, I mentioned versatility. I mentioned we can always reduce down to the chi-squared. Recall, if we go from continuous to categorical to use the chi-squared, we do lose some information. So I mentioned that. I should probably add that caveat that it's not always a good thing to do. It can be very useful. It can be very useful a lot of the time, but we do want to be careful about doing that to make sure that if we are doing that, we are doing so in a way or at times when it's necessary, and not doing so if we had a continuous analytical option available, because it is going to have less statistical power in that case. That is less of a chance to find a difference if it's actually there. All right, so this will be our last slide here. I just want to quickly mention some extensions that we can do to build on this, because we don't have time to discuss all the different methods possible for categorical data. And again, we don't even time to discuss all the important ones. So I wanted to talk about a couple of possible extensions that you may hear about. One is log linear models. I mentioned we can do categorical data analysis with more than 2 variables, or the chi-squared with more than 2 variables, and we can. But often what we do with more than 2 variables is something called log linear analysis, or a log linear model, which handles multiple categorical independent variables. The reason log linear models may be better than just doing a chi-squared analysis with multiple variables, with 3 or 4 different categorical variables, is a chi-squared kind of tells you there's a difference somewhere, where a log linear model can really help you get at, okay, where is the difference in a little bit of a more precise way. Another option you may hear about is discriminant analysis. This is useful. So log linear models are useful if I have multiple categorical variables. Discriminant analysis is useful if I have a categorical outcome, but multiple continuous variables, which are normally distributed, and can be handy. Logistic regression is kind of a more generic. It kind of I shouldn't say combines it. It statistically doesn't, but maybe ideologically does. Log linear models require categorical independent variables and a categorical outcome. Discriminant analysis requires continuous independent variables and a categorical outcome. Logistic regression can handle both categorical and continuous independent variables. Doesn't necessarily require the continuous independent variables to be distributed normally. So logistic regression is actually a good general choice. As we discussed, the problem with logistic regression is the interpretation. And that can be very complex. But the logistic regression is a very standard choice. The interpretation is typically done in terms of exponentiated odds ratios, which are about as fun as they sound. So yeah, we have to take parameter estimates. I guess they're logarithmed odds ratios, and we exponentiate the parameter estimate to get the odds ratios. Are all multiplicative. It's kind of a nasty interpretation, frankly. But you can get big picture interpretations, like this has an effect, or this is statistically significant. You can get the direction positive or negative. It has a positive or negative effect. Those can be pulled out of a logistic regression pretty easily. The nice part is, and the reason a lot of people use it, is it's generic. It can handle different kinds of independent variables, different kinds of dependent variables, and it can handle different kinds of independent variables, categorical and continuous, and can handle categorical dependent variable. Logistic regression by default handles binary dependent variables. That's dependent variables that have two options. But it can also handle dependent variables that have more than two levels. And in that case, we tend to call it multinomial logistic regression to indicate that we're doing a logistic regression with more than two outcome possibilities. One thing that we're not going to have time to talk much about in this course, but is actually a really important thing, especially in medical research, is something called repeated measures. That is when we're studying the same data over time. This is really important, and sadly, as we're kind of laying the groundwork, all of these analyses that we're going to discuss in this class have repeated measures extensions, and we're just not going to have the opportunity to get into them. So for each one in the extension, we're going to have something that you could talk about, or we're going to have some things that you can look more into. And for all of them, repeated measures is going to be one. So in this case, one of our categories would be something like pre-post or data over time, where individuals in each column are the same. And that's where we'd use this. So for instance, we could do something like, do you like our product? And then have them watch a video and on how amazing the product is, and then ask, do you like the product again? And see how many yeses or nos change. All right, this is an extension, and it is in some ways, but and we kind of mentioned it, but the detailed follow-up on where differences lie, how big they are, measures of effect size, etc., that is something that you can really dive deep into. We kind of illustrated a little bit of this in a way with the confusion matrix. We talked about all the different information you can pull from the tables. This is kind of like that, but in its own way, very, very different from that. So it's a bit analogous. I guess the thing that it's kind of like that in the way of is these tables have lots of information that you can pull out of them. There's a lot of different ways that you can extract the information on where differences lie and how big they are regarding a detailed follow-up for a statistically significant finding. We didn't talk too much about that in this lecture set and don't really have the opportunity to. I will say one of the articles that you will read for this section does talk about a more formal analysis called Kramer's V regarding the effect size. But again, this is not something that we hit in this lecture video or this lecture set. We did talk a little bit about it. We talked about looking at the contributions to the chi-squared statistic from each cell, then looking for the big ones, and then backtracing those to the difference between observed and expected. This is good and very useful, and it's a good kind of stopgap as we didn't talk about the more detailed measures. And I think you can definitely, that has a lot of legs. You can get pretty far with that. But more detailed could provide more detailed information on what is big, what are the biggest contributors, one is 10, one is 8, one is 4, are all of these big or some bigger? Is the one that's 10, 2.5 times bigger than the one that's 4? And in a way it is, and in a way it's not. So again, we didn't discuss too much into that detailed follow-up. I think the method we did demonstrate in class is pretty generally useful, but there is more information that you can go and find regarding an extension of that if you're interested. All right, so that wraps this up for this lecture set on the chi-squared analysis. We talked about the chi-squared analysis, contingency tables, confusion matrices, the chi-squared goodness of fit test, and the chi-squared test of independence. And in the next videos, we'll be talking about how to do a couple of these things in software.